Hey folks, good evening. How we doing? This is Mr. Murray coming to you with a video on division and radicals. Okay, so in this video I'm going to talk about all different kinds of things involving radicals, from simplifying them to rationalizing the denominator. All right, those are the two big skills we talked about, and throughout this video there's going to be opportunities for you to try and for me to show you how to do it. I encourage you to work your way through this and to try the problems so that you can really build up your skills on this important concept, okay? So first I'm going to start with simplifying, okay? So when we simplify, all right, what we're looking to do is we're looking to first take care of any numbers, and then we're looking to go inside and simplify the radical any way we can. Sometimes you can simplify the top or the bottom. Like for example, I can already see this is 2 or 4 root 2 because this is 16 times 2. Or you can also, so long as the index is the same, which in this case it is, you can also divide and clear up the square root like that. So I'm going to show you how we do this one. Okay, so the first thing I'm going to do again is I'm going to simplify. I'm going to work on the numbers. Okay, so I've got a 7 and I've got a 14. It's going to simplify as 1/2. Okay, and I'll do it in pencil and then I can trace it over as well so you can see our final answer. But you know, mistakes are okay. Now I'm going to look at the roots. So again, the indices are the same. So I'm going to now divide within the root, because the square root, a square root divided by a square root is the same as putting everything inside the square root and then dividing, right? So that means it's the same as the square root of 32 divided by 2. Okay, and then a to the 5th divided by a to the 3rd. All right, and now I'm going to go ahead and simplify. Okay, so I'm going to do the square root of 16. So it's 1/2 times 4 is the square root of 16. Remember, we're sticking with the positive because we're simplifying. Okay, and the square root of a squared is a. Okay, and then we clean it up. Okay, and our final answer is going to be 2a. All right, so again, step by step. Numbers. Okay, do the division of the roots and clean up as needed. Okay, now I'm going to show you what it looks like when we're working with what we have here, which is a cube root. So the cube root's the same idea. The first step, okay, is going to be to do some division. So again, notice the indices are the same. So because of what we call the quotient rule, with regard to radicals, I'm now going to do the division. So I've got negative 54 divided by negative 2. A to the 7th divided by a squared. B to the 13th divided by b to the 5th. Okay, we need to understand at this point the laws of exponents, okay? Sophomores, this was talked about last year, okay, in course 1, the laws of exponents. When you divide a power, or rather an expression with an exponent by an expression with an exponent, if the bases are the same, you need to subtract the exponents, okay? I gotta assume you know that. Now let's clean up. So the cube root of 27, 3. A to the 5th, we're going to split that. That's going to be a to the 3rd times a squared. And b to the 8th, that's going to be b to the 6th times b to the 2nd. Remember, okay, we target the power of 3 and the power of 6, because when we take the cube root, we're going to end up with a whole number, or rather a whole number for the exponent. Okay, so when I do the cube root of a cubed, I get a. When I do the cube root of b to the 6th, I get b squared. And then what's left under the cube root is a squared b squared, which is not, here's a little math joke, not equal to c squared. Haha, those Pythagorean theorem lovers there. So I got 3a, b squared, and just be really careful how you do your indices here, but that's a cube root. Now remember, the big question I get is this, Mr. Moray, but look, 8 doesn't have a cube root, or a cube root of 8 is 2, right? So why is that going on? Remember, when you're doing the cube root, you're not trying to cube root the number. This is an exponent. You need to see if the exponent is divisible by the index. If the exponent is divisible by the index, okay, you just straight up divide like we did up here, right? 2 divisible by 2. But if the exponent is not divisible by the index, you try your best to split it up such that you have 2 powers of the letter that add to the original power, but such that one of them, right, will be divisible, just like with the 27, or just like with the 16 or 32, right? Here's a good example, right? So 32 doesn't have a square root, but a number that goes into 32, namely 16, does, right? b to a to the 5th doesn't have a perfect cube root, but a to the 3rd, which goes into a to the 5th, does. All right, now I'm going to come up with a little u try here. So what I have is 25 times the 4th root of 80 x to the 12th y to the 15th over negative 5 times the 4th root of 5x to the 4th y to the 10th. Go ahead, try to simplify this, okay? Pause the video, and then when you unpause, I'll show you how to do it. All right, so let's do this one step at a time. Remember, the first step is to do what? The first step is to divide the numbers. So I've got 25 divided by negative 5. That's negative 5. Second step, let's clean up inside of the root. So inside the roots, notice indices, are they the same? Yes, so I'm now going to clean up. So times the 4th root. And see, if you stick the 4 right in this little crevice here, then I'll know that you're talking the 4th root. Now, 80 divided by 5 is 16. 16, 32, 48, 64, 80. Okay? So that'll become 16. X to the 12th divided by x to the 4th. That's x to the 8th. Y to the 15th divided by y to the 10th. That's y to the 5th. All right. Hopefully we're able to see that all right. So I'm going to pen it out from here. So we got negative 5 times the 4th root of 16 x to the 8th y to the 5th. Now, let's see what we can do. So let's look at the 16. Does the 16 have a perfect 4th root? It does. 2, 2, 2, 2. That's equal to 16. Okay, therefore, what I have is negative 5 times 2. Now, is x to the 8th? This is x to the 8th. Does x to the 8th have a perfect 4th root? It does. It's x squared. Does y to the 5th have a perfect 4th root? It does not, but notice I get y to the 4th times y, and y to the 4th has a perfect 4th root. So I pull out the perfect 4th root by multiplying the exponent times a quarter, because it's basically y to the 4th to the quarter, right? And when, again, laws of exponents, they multiply, okay? Times the 4th root of y to the 1st, or just y. So we combine them all. I get negative 10 x squared y times the 4th root of y, okay? Now, I like to always do this by taking the letters and arranging them alphabetically. This is also known to some as what you might call lexicographic ordering, or dictionary-based ordering. I always say, please try to keep things nice and neat and organized and arrange these kinds of expressions in order by alphabetical, right? So the X, then the Y, then the Z, right? If you have, unless, here's the one example, unless I don't present it to you, like I've done H and then B as my two letters, that would be an exception. But if you can, try to put it in alphabetical order. The order of the letters isn't super important, but it's like a nice thing you can do for me. Okay? Okay, so now I'm going to move on to the next skill that we talked about, and that is what's called rationalizing the denominator. Okay, and I'm going to show you a couple different examples of how we do that. So remember, this is the idea. So there's a lot of numbers like the square root of 2, like pi, like, you'll learn e, the square root of 18, okay, that aren't whole numbers. And not only are they not whole numbers, but their decimals go on and on and on forever, and they never really stop. Now, we talked about this when we simplified with I in the denominator, and we were like, look, this I stuff, this isn't even a real number. We don't even want to divide by this stuff because this isn't even real, right? It's imaginary. So similarly, if we have a number like the square root of 2, it's like 1.412, blah, 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 blah. We don't want to divide by something that's going on forever. And multiplying by 3 in this case, or 2 in this case, it doesn't make the number any better to divide by, okay? And so when we have these numbers that go on forever, and technically speaking can't be represented as a ratio, that's what rational ratio. So like numbers like the square root of 2 can never be represented as a number, an integer divided by an integer, right? A positive, negative whole number divided by another positive or negative whole number. That'll never happen. So what we're going to do is, we don't like that. We're going to try to do what we call rationalizing the denominator. And what we're going to do here is, our goal is to eliminate any square roots we don't like from the denominator. Now, I've shown this a couple ways. One way in this case, so this is what I'd call case 1. Okay? In case 1, there's what we call a monomial down in the denominator, which means it's only one thing. So case 1, monomial, one thing. 3 square root of 7, one term, right? Remember, we said nomial, meaning number. Okay, there's only one number here, in that it's 3 square root of 7. So there's two things you can do. You can either multiply by everything, technically will work, or you can multiply by the square root of 7. I'll show you both ways. So I'm going to first multiply by the square root of 7 on the bottom. Now, to keep the fraction equal to the original value, I'm also going to multiply the top by the square root of 7, right? Because when you do the same thing to the top and the bottom, the fraction's value doesn't change, it just looks different. So here's what we get. We come across the top with 2 times square root of 7, and that becomes 2 square root 7. Now on the bottom, we have 3 square root 7 times, in theory, this is 1 square root of 7, right? It's just square root of 7. So the 3 and the 1 come together, you get 3. And the 7 and the 7, well, when they multiply, you get the square root of 49, which is 7. And so remember, when you're working with square roots, when you take the square root and you multiply it by another square root and the numbers underneath are the same, they cancel out, right? And we're going to talk about this idea of inverse operations. That's something we're going to actually get at a little bit later in the current unit. So what we have is, we have 2 square root of 7 over 21. And that's as simplified as we can get it. Here's the other option. So the other option would be to multiply by the whole denominator. I mean, that's all right too. I'm just going to show you it's going to require one more step. So let's say I'm like, look, I don't know. I want to be safe. I want to multiply by the whole denominator because I know it's going to get everything to go away. So watch what happens. Up here, we have the 2 times the 3 giving us a 6. We have this no square root times the square root of 7. We get a square root of 7. Down here, I get 9. And then I get 7, right? Again, times the square root of 49. Okay, and it's 6 square root of 7 over 9 times 7, which is 63. Now what I observe is I say, look, can we reduce this? Is this simplified? So notice, because there were no common factors, I got an answer that was simplified. You cannot ever leave a fraction like this because, for example, the top and the bottom are both divisible by 3. I know that because each digit is a multiple of 3. And another way to see it is the digits. 6 is a multiple of 3, and 6 plus 3, which is 9, is also a multiple of 3. So if you want to multiply by the entire denominator, that's fine. You're going to get an equal answer either way. But just remember, if you do multiply by the whole denominator, then you're going to end up having to simplify in the end, and then that could be a full credit issue. All right, so the idea is when you have a monomial, you have to multiply by at least top and bottom. Again, you do the same thing, just like we've always done with fractions when we rewrite them in this way, like adding or subtracting. You do the same thing to the top and the bottom to keep the value fixed, keep the actual value of the fraction the same, and then you mitigate the square root. Notice in the end, the number in the bottom is a whole number, and rather not even a whole number is what I'm getting at, but rather it's a rational, it's an integer, right? So we had the same thing happen with imaginary, complex, right? We'd multiply by a number, a complex conjugate, and when we did that, the number down in the bottom would become a real number, okay? Just like now, it is now a rational number, right? All whole numbers are rational numbers, okay? The only time you get into trouble is with rationals, generally speaking, is when you deal with square roots, with the exception of numbers like e and pi and stuff like that. All right, now I'm going to come down here. So I've got negative 5 over 2 root 13. All right, take a second, really quick, think about what would you multiply the top and the bottom by? I'm going to multiply the top and the bottom, in this case, just for time's sake, by the square root of 13. Notice it's a monomial, one number, 2 root 13. Another way to look at this, theoretically speaking, is you could bring this all in one root. And if you did bring it all into one root, it would be, in this case, 4 times root 13. So that's the square root of 52. You can think about it that way as well. I'm going to multiply top and bottom by just the root of 13. If you do it by 2 root 13, you're going to get the same answer. So up top, you multiply straight across. On bottom, the 13s cancel out. Or rather, the roots cancel out. So you get negative 5 root 13 over 26. You ask, can I simplify this anymore? You cannot, okay? Other method. What if I'd multiplied by 2 root 13, right? I do it, you know what? I want to be safe. I'm going to hit it with the whole denominator. Then what you'd get is you'd get negative 10 root 13 because you'd have to do the 5 and the 2. Now on the bottom, you'd get 4 times 13, right? So you'd get negative 10 root 13 over 52. But look, it's not simplified because there's a 2 in this and a 2 in that. So you'd have to divide, and you'd end up with the same answer either way. Now, the reason I'm hitting on this is because in the class, we talked about people have come up with multiple different ways to solve these problems. And you know what? I'm completely okay with that, provided that your answer makes sense. You do it that way if that's how you want to do it. All right, I'm going to come up here, and this denominator is already, in this case, rationalized. So I'm going to go ahead and I'm going to throw this radical on here to make it not rationalized. This is just going to be a little bit more difficult because now, okay, we're going to be multiplying by two things instead of one. So here, how do I rationalize this? Ready? Think about this. 3 seconds. What number am I multiplying on the top and the bottom? Ready? 1, 2, 3. It's the square root of 18 on the top and the bottom. Okay, square root of 18. Square root of 18. Let's hit it with a distribution. So here's where it gets harder. So when you remember, when you multiply by square roots, square root times square root, are the indices the same? 2 and 2, yes. I multiply the numbers under the root. So 18 times 5, that is 90. 18 times 6. Well, 18 times 6 is somewhat more straightforward to carry out. If you want to really multiply it, you can. I mean, we know that, this is half of 180. You could really just add on. I mean, if you really wanted to come off to the side, I'm never going to take issue with if you want to do a little bit of column arithmetic. You do what you want. 108. And the bottom, roots cancel, becomes an 18. So we've rationalized the denominator. Are we done? No. Never leave roots like this unless you really cannot simplify them. You've got to make an attempt to simplify these. So let's think about it. Do any numbers go into here that are whole number square root, or that have a whole number for a square root? So let's do our little tree. All right, does 4 go into it? No. Does 9 go into it? Yes. 9 and 10 go into 90. All right. Now, 108. What goes into 108? I can already see that 90 goes into 108. Now, notice when you get the square root of 18, technically the square root of 18 is 3 root 2. So you could have rewritten 18, and I'll show you what I mean in just a second. So I've got 9 times 10, okay, and this is 9. Okay, 108 divided by 9. 9 goes into 10 once. 9 goes into 18 12 times. Okay, and so what that's indicating to me is that there's a bigger number that could have gone in there. And actually, 36 will go into 108 3 times. 36, 72, 108. So I break that down, and I get here 3 root 10 minus 6 root 3 over 18. Now, can I simplify? Well, yes, 3, 6, and 18 all share a factor of 3. So 3 divided by 3 is root 10. 6 divided by 3 is negative 2. And 18 divided by 3 is 9, okay? Can these be brought together? They cannot, because though they have the same index, they have different numbers under the root. So you get square root 10 minus 2 root 3 over 9. The reason I did that initial simplification is maybe in part due to the fact that I didn't do very much cleanup in the beginning. So let me show you what would happen if I started by making this 3 root 2, okay? So that would mean what I'd have is root 5 minus root 6 over 3 root 2. This is an alternative. You don't have to do it this way. So now I'd multiply by root 2 over root 2 to cancel out the root 2's. So I'd get 3 times, the 2's would come together. 2 times 2, the 2's go away, becomes a 2. The roots go away, becomes a 2. 3 times 2 is 6. Oh, yep. And by the way, my quick little fix here. You're dividing by 3, so this should actually become a 6, right? 3 divided by 3, 1, 2, and 6. There's where I'm getting that from. Okay. All right. Anyway, so now I'm going to do root 2 divided by root 5, 10. Root 2 divided by root 6, All right, that's root 12. And then you have to clean that up one step further. Okay, so it's root 10 minus, well, 12 is 2 root 3 because it's 4 times 3 over 6. So notice, exact same answers, just a different way of doing them. So remember, I'm going to let you take a lot of different ways. You know, I saw some people in class like, wait, Mr. Moray, I know I can clean up through root 18. If you rationalize the denominator, 100% cool. But you have to know what you're doing here. And if you come in with a method that, one, is 100% mathematically correct, you execute that method correctly, you get an answer, and you simplify it sufficiently, as long as that holds, generally speaking, you will get full credit. I'm not looking for you to take one path. I'm looking for you to take a path that's mathematically valid and makes sense and gets a simplified answer. Okay? So now I'm going to come to the U-try, and I know we're definitely getting into the time factor. Take a second, try to simplify this with a monomial, okay? And then unpause, and we'll check to see if you were right. All right, I'm excited to see whether you got this one. So here, two options. I'll show you. Option 1, you multiply by just the root. Okay, give me the roots, give me the roots. Because you could multiply by the whole thing. You don't technically need to, okay? So here, I'll distribute. So I get 6 root 2 minus square root of 6. Okay? Then I get 2 times 2. That cancels and becomes 2. 4 times 2. That's 8. Okay? Can I simplify? The 6, can't break it down. There's no perfect square. Okay? It's going to go into 6. The 1 in front of it can't be broken down. I'm really basically done. Let's see what happens if I do it the other way. Okay? So some people say scorched earth, hit it with everything you got. All right, so what I'd get if I did it like this is going to be 24 root 2 because it's 6 times 4 and then the root 2. This is going to become minus 4 root 6. This is going to become 4 times 4, which is 16. The roots will cancel and make a 2. That'll get me 32. Now, as you can see here, there's going to be a common factor. Again, the 6 and the 2, we can't touch those. But the 24, the 4, and the 32 all have a common factor of 2. So I guess, actually, I'll do it up here. So the 24 divided by 4, 6. Remember, when you're doing the common factor, you're only hitting the coefficient. Do not mess with the number inside of the root, okay? Minus 4 divided by 4, that's 1, so it becomes a straight up root 6. Okay, and then you have 32 divided by 4, that's 8. Okay, so a couple different ways to do this. Again, as long as you do a way that's mathematically valid, hitting the top and the bottom with the same thing to keep the value the same. A, the roots canceling. In both cases, root cancels, fractions clean. You do those 3 things, you get to the right answer. I'm not marking you down because I want to see that you have a valid way to do it. Now, one way it could cost you is with regard to time. If I say go, 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 we got to do this quick, this might have an advantage because it gets you there quicker, right? 1 step, done. Here, it's 1 step, clean it up, divide everything, done. So you have another step in it, but mathematically valid nonetheless. Okay, so now I'm going to go into the final examples here. And this is what I call case 2. And that is a binomial, bi like a bicycle, 2, denominator, okay? So in these ones, we have a binomial in the denominator. And with this, you need to use what we call the conjugate, okay? So if I have A times the square root of B and C times the square root of D, okay? The conjugate is going to be, all you do is you just flip the sign in the middle, just like with imaginary numbers. Remember, when we had A plus BI, it would be A minus BI. And remember, when we multiply them, every single thing, okay, that had an I, gone. Same thing we're going to see here. Anything with a root is gone when you multiply by the conjugate 100% of the time. Let's take a look. So we look here. This is rather simple. The conjugate here, 4 root 3, opposite sign, plus. This comes back to the idea of difference of squares. So remember when we multiplied difference of squares, it was like the only thing that was left was like the square of the first thing minus the square of the second thing. Same idea. So when we multiply this out, I'll show you a quick little foil, so to speak. We get 16. We get plus 4 root 3. And the minus makes sure we then have minus 4 root 3. Okay? Minus the square root of 9. In other words, the square root of 3 squared. Okay? So if you think about it, these cancel. So I have 16, and then the square root of 3 is 9. So all I've left is 13. So notice how the conjugate always ensures that there is no number left in the bottom that is not a square root. Okay? And similarly, what I do to the bottom, I do to the top. So we now know that the bottom is 13. Now I just multiply. So 12, 24, 36, 48. Plus 12 root 3 all over 13. Okay? Now I look. Can I clean it up? No. 13 is prime. Can't touch this. It's prime. Okay? Can I touch this? Nope. Square root 3. Can't touch that. 48. It's a number. Can't really mess with that. Okay? So that's the idea. You're hitting it with the conjugate. You're distributing. Now, the distribution on the top, the distribution on the bottom, it's like you're good because the distribution on the bottom, you're always going to get, you should always get 100% of the time. You better be getting a whole number. If you didn't rationalize the denominator, you're out of luck. Top-wise, it's going to vary. Okay? Now I'm going to come down to this next one. A little bit harder because you got a root. But let's see what happens. First, hit it with the conjugate. 6. What's next? Minus. And the root, 2. Okay? So when I do this, 36 minus 6 root 2 plus 6 root 2, so you see the cancel, minus 2. So it's 36 minus 2. 34 in the denominator. Up top, I get 6 root 5. The tough thing is you're distributing, it depends how you distribute. Remember, you always put the number before the root. Here, minus 2 times 5 comes back in the root of 10. Okay, let's take a look. 5, can I break it down? No, can't touch that. 10, can I break it down? Now, some people are like, yep, 5 and 2, but you can't do a 5 and a 2 because the 5 and the 2, neither of them are perfect squares. You can't break that down. What about, can I divide everything by 2? No, because the 6 is divisible by 2, the 34 is divisible by 2, but the 1 is not divisible by 2. So in this case, it seems like you're good to leave it. All right, so the next one, the last one, is one where it's a little bit tougher distribution. Same idea, except you have to do a little bit of what we'd call foiling up top. So notice how the roots are the same. Sometimes you're going to get a smorgasbord of roots, so to speak, and sometimes the roots will be the same. The more different roots you have, the more complicated and your answer is going to look. But remember, a complicated answer is not necessarily an incorrect answer, okay? So on the bottom, I'm going to get 9, 3 times 3, minus 7, because those are the roots. So I'm going to get 2. If you're confused about how to do it, let's do a quick little box, okay? I love to see this in class today. 3 minus root 7, 3 plus root 7, okay? 9 minus 3 root 7, plus 3 root 7, so those cancel, okay? Minus the square root of 49, which is minus 7. 9 minus 7 is 2. And remember, should be gone, nothing in the denominator. Okay, now let's do the top. I'm going to box the top. 2 plus root 7, 3 plus root 7. So let's take a look. 2 times 3, 6. 3 root 7. 2 root 7. Square root of 49, which is 7. So I get 6 plus 7, 13. 3 root 7 plus 2 root 7. Are the roots the same? Both square. Are the number in the same? Yep, both 7. So that's what I'm talking about. When you see only one kind of root, you're going to be okay. When the roots start to differ, that's when you're going to run into problems. And the more different roots you have, the more complicated looking it's going to be. In the beginning, we'll try to keep it more straightforward, but then we'll slowly build up and make it more and more complicated. All right, time for a little you try. So I've got 2 right here. Okay, so I've got 10 over 5 plus 2 root 2. I've got 6 plus 5 root 2 over 4 plus 3 root 2. I want you to take a second, simplify, rationalize those denominators, okay? And then pause the video, rationalize them out, then unpause in a few seconds. Once you're done, I'll show you how to do them. All right, I love these. Let's take a look at this. So first, you're going to hit it with the what you get. Get it? What'd you get? The conjugate. All right. So, conjugate. What'd you get? The conjugate. Yeah. Okay? That's the conjugate. You got to do that. Now, what we get when we do the conjugate, that's where it's going to get tough. So, if you're confused with what the conjugate's going to turn out to be, I recommend off to the side you actually figure it out. So, 5 times 5, that's 25. We only have to worry about the 5 squared and then this squared. So, I'm going to drop my minus because I know it's going to be negative. It's a positive and a negative. The 2 and the 2, 4. The root 2 and the root 2 becomes a 2. So it's 25 minus 8. That would be 17. Okay? So my final denominator, 17. Now up top, distribute 10 and 5. That's 50 minus 20 root 2. Okay. So let's see. 50, can I simplify it? No. 20, can I simplify? No. Okay, so that means I'm as simplified as I can get. Okay, so quick recap. 1, hit it with the conjugate. 5 minus 2 root 2. Do them out. Do out the FOIL, so to speak. Okay, so the 5 and the 5 give me the 25. Here, 2 times 2 is 4. The roots cancel. You get another 2. That's 8. 25 minus 8, that's 17. Okay, remember, worst case scenario, box it. Okay, so if you know what you're doing, it just saves you time. It doesn't mean that boxing it won't get you the right answer. So right here, you'd get 10 root 2. Here you'd get negative 10 root 2. So they'd cancel. And then here you'd get 4 times the root of 4, which is 4 times 2. And it should be negative, so it's negative 8. So 25 minus 8. Okay? Lastly, let's take a look. So I'm going to multiply by, what's the conjugate? What'd you get for the conjugate? 4 minus 3 root 2. Okay. Down here, 16 for the 4s. Minus, the 3's come together, 9. The 2's make a 2. I should say the root 2's. So I get 16 minus 18. And that's negative 2. That's going to happen sometimes. Sometimes you are going to get a negative as your final answer on the bottom, and that's perfectly okay, so long as you're able to correctly make sense of that in the final fraction, okay? Now here, let's do some multiplying out. So I get 24 minus 18 root 2, okay? plus 20 root 2. Here's the complicated part. So minus 15, because that's 5 times 3. And then in the roots, you get the square root of 4. And we know that's 2. So basically, this whole thing is minusing 30. So we've got 24 minus 30. Okay, let's start with that. 24 minus 30 is negative 6. I'm coming down here. My apologies. Now I've got negative 18 root 2 plus 20 root 2. Are the indices the same? Yes. Are the radicands, the numbers in the roots, the same? Yes. So I get negative 18 plus 20, which is 2 root 2, all over negative 2. I do my final check. Can I touch this? Da-na-na-na. Na-na. Can't touch this. How about this? Da-na-na-na. Can't touch that. Can I clean it up? Yes. They all are divisible by 2. I'm going to divide everything by a negative 2. So if I divide this negative 6 by negative 2, I get 3. If I divide this by negative 2, I get negative 1, so it becomes a minus root 2. And then the bottom, I divide negative 2 by negative 2, I get 1. So it's just 3, because of what we know about fractions, 3 minus root 2. Alternatively, if you just divided it by 2, you're like, whatever, I don't really care that much. I'm just going to do what's comfortable for me. You would get, okay, negative 3, okay, plus root 2 over negative 1. Now, that would be a problem because I wouldn't leave the negative 1 there. So that's where you'd run into problems. But then you could just then flip that as 3 minus root 2. But remember, you shouldn't leave a 1 or a negative 1 down in the denominator. That's not the right thing to do. It's not really simplified. We know when you divide by 1, it's the same thing as just this thing up there. Okay, so really be careful with that. Okay, so I hope you found this video to be informational. And I know that it definitely went into a good amount of time. So I really appreciate your patience. I'll definitely try to put some timestamps on this to cut this through a little bit faster. But again, I really appreciate, those of you who are able to get through this, to really take the time and make sense of these difficult problems. I know the radical stuff's not easy, but if you're willing to put in the time to go through these videos, you will find, hopefully, that they'll help you get there, okay? So remember, keep thinking about the ideas, keep asking questions, keep them coming, and remember, you can do it. All right, so thanks very much for watching this video. Don't forget to keep loving math, and have a wonderful day.